Okay, everyone hear me okay? Well, thank you for the introduction, and thank you to the organizers. For those of you like me who haven't organized a conference with 300 or 400 participants and hundreds of contributed talks, you may not appreciate what a monumental effort is involved in managing the logistics of all this. And I'm very grateful to and in awe of Gabo and Antonella for taking this task on. So thank you, and we look forward to a very exciting week. Okay, so I'm going to talk about L functions from nothing. Now, my guess is, for a number theory audience, I don't need to say too much about what an L function is or why you should be interested in them, but probably I need to say quite a bit about what I mean from nothing. But nevertheless, let's start with L functions. So many of the most important questions in number theory involve L functions in some way. The first four of these, for the first four of the items I've listed here, these are very explicitly about questions of zeros or special values of L functions. The next three, the Sauterté conjecture, Lang-Trotter conjecture, and very recent work on murmurations, might not immediately have an obvious connection to L functions. They're about distribution of Frobenius traces, but those Frobenius traces show up as the Dirichlet coefficients of L functions. So in some very tangible sense, they really are questions about L functions, and they can all be generalized to a very general setting that's purely about L functions and that doesn't necessarily assume anything about an underlying source of the L functions. And maybe the most, at least for me, the most compelling reason to be interested in L functions is modularity and more generally the Langlands program. Again, I expect this is familiar, at least some portions of this diagram are familiar to almost everybody in this room, but I'll just recall that sort of the overarching theme of the Langlands program is it gives us a bridge between two different worlds, the automorphic world of automorphic representations and automorphic forms, and what I'll call the motivic world. But if you want to think about this more, these are typically objects in arithmetic geometry. Very concretely, things like curves, abelian varieties, and other sort of arithmetic geometric objects that give rise to L functions and Galois representations. And those both give us ways to connect these motivic objects to objects in the automorphic world. And the Langlands program is really a series of conjectures that makes that speculates that under suitable constraints, defining exactly what class of objects you mean in the automorphic world and what class of objects you're referring to in the motivic world, there should always be a connection between these objects, both via an L function that one can associate and also via Galois representations. In this talk, I'm going to really focus on the top box in this figure, the L function box, because in some ways it's the most sort of tangible, explicit, hands-on aspect of both automorphic forms and motives that we can get our hands on. So automorphic forms can be and automorphic representations can be very complicated things, and motives can also be very complicated. But every L function, or at least all the L functions we're going to be interested in today, can be described by a sequence of integers, an infinite sequence of integers. Okay, so easy to understand. And one perspective I like to take on L functions is they serve as sort of a DNA that this sequence encodes something essential about the objects that share the same L function. And so it's a natural place for us to focus. And it's also sort of the underlying motivation and design principle for the L functions and modular forms database, which again, I'm sure many of you are familiar with. If you haven't seen the LMFDB before, I encourage you to go visit www.lmfdb.org. You can find an animated version of this diagram, including additional information you can get if you hover over any of the boxes or any of the arrows in this diagram if you'd like to learn more about what's going on there, and also links to objects that explicitly realize different parts of this diagram That's really why the LMFDB exists and what it's all about. And sort of the shining example or the shining success of the Langlands program, and one of the, at least in my view, preeminent results of 20th century number theory, is the proof of modularity of elliptic curves. This is a result of a long series of effort by many people, but perhaps most notably Andrew Wiles, and work by Richard Taylor and Andrew Wiles to complete the proof of this theorem, at least in the case of, in one special but sufficiently case that's sufficiently general to include as a corollary the proof of Fermat's last theorem. And then sort of the final nail was put in by Burrell, Conrad, Diamond, and Taylor, who proved modularity for all elliptic curves over Q. And the statement of this theorem is simply that for every positive integer n, the set of L functions of elliptic curves over Q with conductor n is the same as the set of L functions of classical modular forms that are normalized eigenforms, so new forms of weight 2 and level n that have rational Q expansions. And one thing I'd like to emphasize at this point is that, and you can see it in the picture, this runs in both directions. I mean, we tend to, because it was sort of the last hardest step, we tend to think of the direction that says that every elliptic curve, the L function of every elliptic curve over Q corresponds to the L function of a modular form. But the other direction is also highly non-trivial. I mean, it was proved much earlier by Eichler and especially Shimura that you can associate to the Gauss orbit of any new form an abelian variety. And in the case when that new form has rational coefficients, that's an abelian variety of dimension 1, which is an elliptic curve. And you can do this very explicitly. If I give you the Q expansion of a weight 2 modular form with rational coefficients, there's a very explicit procedure that will let you compute a distinguished elliptic curve, which is a representative of an isogeny class of elliptic curves that share the same L function. But that has some non-trivial consequences that are maybe not as widely appreciated as they should be. For example, without one half of this theorem, it's not at all obvious that this set of L functions of weight 2 modular forms with rational Q expansions is infinite. There's no reason that it might as well be finite. As the spaces of modular forms get bigger and bigger, absent some fundamental reason why the space should decompose into hecastable, into pieces that are stable under the action of the Heck operators. Once those spaces get big enough, all of those subspaces are also quite large, and there's no reason a priori to think that there should be a one-dimensional piece. And in fact, if I change 1 to a slightly larger number, like 7, it's generally believed that there are only finitely many weight 2 classical modular forms whose Hecke coefficient field has degree 7. And that's true for every number greater than 7 as well. It's only for the small numbers that we actually have any reason to think there should be infinitely many. And the only case where there's a really explicit theorem proving that is the case where the dimension is 1. This will be an important point when we want to generalize this theorem to higher dimension. So long before the modularity theorem was completely proved, I mean, the last step of this proof wasn't completed until the year 2000, right at the end of the 20th century. Under the assumption that this theorem was true, it allowed people to construct tables of the objects on both sides of the modularity theorem. So elliptic curves over Q on the one side. These were tabulated by a number of different people, but most notably by Swinnerton Dyer, and there's the tables of the elliptic curves he tabulated are included in the Antwerp tables, and also modular forms that were compiled by Tingley. And it's worth noting that it was very important that we had the table of modular forms to check, because it actually pointed out a number of elliptic curves that were missing in the initial tabulations. In fact, it's extremely, without using modularity, it is extremely difficult, and even today, really an unsolved problem, to enumerate elliptic curves over Q ordered by conductor. The only reason we can do that is because we can enumerate modular forms by level and then find a corresponding elliptic curve and then enumerate all the elliptic curves in the isogeny class. Okay. Now there is a more modern version of these tables is now available in the LMFDB. So you can go list elliptic curves over Q ordered by their conductor, and you can go and list weight 2 modular forms with rational coefficients ordered by level. And as long as you group your elliptic curves into isogeny classes, the tables will match up perfectly. You can connect every line of these tables. And I've only shown you these tables up to 39, but in fact, they extend currently up to 500,000. And we are in the process of extending them further all the way up to 1 million. Okay. So now we want to move beyond dimension 1, beyond elliptic curves and classical modular forms. And in order to do so, I want to introduce sort of an analog of the modularity conjecture, now a theorem for elliptic curves, for abelian varieties. Of course, the Langlands program is much larger than that, and one can state modularity conjectures in a much broader context. But for this talk, we're going to focus on L functions of abelian varieties. So just recall, an abelian variety is a smooth projective variety that is also an algebraic group. That means the group law is defined explicitly by morphisms. Fun fact, you don't actually have to include the abelian part in the definition. As soon as you insist that your variety is your algebraic group is actually defined by a projective variety, that forces it to be abelian. You may be more familiar with algebraic groups that are not projective, and there's a whole theory associated to those as well. And as I mentioned earlier, elliptic curves are abelian varieties of dimension 1, but abelian varieties of every dimension exist. And we'll generally use the symbol G to denote the dimension of the abelian variety. You might wonder why not use D, but the reason to use G will become clear in a moment. Yeah, spoiler alert, G is often used to denote the genus of a curve, and the Jacobian of a smooth projective curve is an abelian of genus G is an abelian variety of dimension G. Okay, and so we're always working in the category of abelian varieties of some fixed dimension over some fixed field K. And for the rest of this talk, the field K is going to be Q, but I'll try to state things more generally than that in places where I can. The morphisms in this category are called isogenies, and these are surjective morphisms of algebraic varieties that have finite kernel and are compatible with the group structure. Now, for every G greater than or equal to 1, if K is a number field, we can associate to each abelian variety of dimension G over K an L function. And the L function of the abelian variety is defined in terms of an Euler product, which then gives you a Dirichlet series. The factors appearing in this Euler product, or at least the denominator of the factors appearing in this Euler product, are called L polynomials. They're polynomials with integer coefficients and degree at most 2g and generically exactly equal to 2g. That will be true at all but a finite set of primes. And the Dirichlet coefficients, the a sub n, are always integers. So when I'm referred to this sequence of integers, this is the sequence of integers I'm referring to. If you know the sequence of integer Dirichlet coefficients of an L function, you know everything you need to know about that L function. Mostly, I'm slightly lying there, but if your L function is the L function of an abelian variety over Q, what I just said is true. And you may also be familiar with these L polynomials in another context. If you work with abelian varieties or with curves over finite fields, they appear as the numerator of the zeta function. And a fact that will be important to us is that two abelian varieties over number fields have the same L function if and only if they're isogeny. One direction of that fact is due to Tate, and the other direction, which is highly non-trivial, is due to Faltings. So in some sense, we can identify L functions of abelian varieties over number fields with isogeny classes of abelian varieties over number fields. And then the generalization of the modularity conjecture for elliptic curves says that every abelian variety over number field is modular. And what does that mean? Well, I'm just going to say explicitly what it means in the case where k equals q. It means there is an automorphic representation of GL2G over the ring of Adels of Q, for which the L function of our abelian variety is equal to the L function associated to this automorphic representation. And I'll just note that in this equality, on the left-hand side of this equality, the L function of the abelian variety, I'm always using the arithmetic normalization, where the Euler factors are literally the L polynomials that appear in the Euler factor are literally the numerator of a zeta function, at least at the good primes. And that means for an abelian variety, the central value of the L function occurs at s equals 1. But if you're an analytic number theorist, or in general, if you're working with automorphic representations, it's much more common to normalize your L function so that the central value is at 1/2, just like as it is with the Riemann zeta function. And so this is why on the right-hand side, I'm using the analytic normalization. I'm writing s minus 1/2 rather than s. But I could also switch the L function of the abelian variety into its analytic normalization if I wanted to. And if you go to the home page of an L function in the LMFDB, there's a little button at the top where you can switch back and forth between the arithmetic normalization, the analytic normalization, depending on whether you feel more like an arithmetic geometer or an analytic number theorist on any particular day. Okay, but I just intentionally used both normalizations in this statement because I want to just emphasize that there are two ways to think about this, and to make sure that the analytic number theorists, of which I am not one, don't complain about some of the things I say later on, because I am as an arithmetic geometer, always going to want to be thinking in the arithmetic normalization. Fortunately, my partner in this work, whose name appeared on the first slide, but whose name I didn't say out loud, is Andy Booker at the University of Bristol, is an analytic number theorist, and is very good at keeping me honest and making sure all the statements we make about L functions are actually true. The other thing I want to say is, I guess two more things I want to say is, one is that in some sense, this conjecture can be made vastly more precise than I've made it. By throwing in GL2G here, I'm sweeping under the rug the fact that there are lots of things you can squeeze into GL2G. And I'm not assuming that these automorphic representations are necessarily irreducible. So for example, a product of elliptic curves would have representations that are really representations of GL2, but if I took two of them, I could take their product and I could squeeze two GL2s into one GL4, for example. And that's just the first of a whole zoo of different things, different games one can play and still wind up inside GL4. I'll say more about that in a little bit. But this is, I think, the cleanest way to get a statement that actually fits in two lines. One can generalize, one can replace Q here with any number field, and one gets a conjecture that we still expect to be true, but it's not quite the right conjecture, simply because when you're not requiring that K to be Q, an equality of L functions is not, you have to say what you mean really by an equality of L functions. To say that they have the same integer Dirichlet coefficients is not really as sharp as you would like it to be. What you'd really like to say is that they have the same Euler product, where the Euler product is actually, indexed by primes of the number field, not primes of Q. And it is possible to have L functions of, abelian varieties over different number fields wind up having the same L function. And one would really like to distinguish those cases. But the good news is for K equals Q, we don't need to worry about that. All right. Maybe this is a good time to pause for any questions. Okay, I will carry on. Okay. So I noted earlier that even prior to proving the modularity theorem, people were tabulating abelian varieties of dimension 1, elliptic curves over Q. And a lot of this work was led by John Cremona, who, the LMFDB is just the latest instantiation of what, for many of us grew up with Cremona's tables, a sort of a standard reference work that we referred to on an almost daily basis. But John Cremona was very happy to have those tables incorporated into the LMFDB, and he's on the editorial board of the LMFDB, and he is diligently engaged at this very moment in extending those tables beyond level 500,000. But let me just recall the algorithm at a very high level for how would you go about constructing a table of elliptic curves over Q ordered by conductor. Well, you might, step one, but you're allowed to skip this step, would be to prove modularity, so that you know that you can actually, instead of enumerating elliptic curves, instead enumerate modular forms. So for each increasing integers n, you want to look at the space of weight 2 modular forms of level n, and we can just focus on the new forms because we know the old forms already showed up for a smaller value of n. And we can restrict our attention to the new forms that have rational coefficients, and that's a big help. And for those of you who want more details on this, I refer you to Cremona's book on enumerating modular elliptic curves, which explains all sorts of clever tricks one can use to sort of pluck out the new forms with rational coefficients in a way that's more efficient than potentially having to enumerate all the modular forms, weight 2 modular forms of level n. And then once you have your hand on a modular form with rational coefficients, one can use the Eichler-Shimura correspondence to explicitly construct a representative of an isogeny class of elliptic curves of conductor n. And then it's simply a matter of filling out the isogeny class by finding all the rational isogenies that your chosen representative admits. And that's a straightforward thing to do. And we know how to do that efficiently. And if you carry out this algorithm for n up to 500,000, you wind up with a bit over something slightly more than 3 million elliptic curves and a bit more than 2 million distinct L functions, which is also the same as the number of distinct isogeny classes. Okay, so this talk is really about what happens if we replace 1 with 2 in this slide. So because we would like, we have a good handle on what happens with elliptic curves over Q. The next obvious step would be to change 1 to 2 and think about abelian varieties of dimension 2, abelian surfaces defined over Q. And it would be great to have the same thing, a table of abelian surfaces over Q and a corresponding table of modular forms that match. Unfortunately, each of these steps is dramatically more difficult when you increase G from 1 to 2. Remarkably, the step that you might have thought was the most difficult, step 1, is arguably the one on which we have made the most progress. And in fact, some of that progress is very recent. There's a paper that was posted to arXiv, I think in February, by Boxer, Caligari, Guy, and Poloni, which proves that a positive proportion of abelian surfaces in some suitable ordering. For example, one could take abelian surfaces that arise as Jacobians of genus 2 curves over Q, where you order the curves by the size of their coefficients. A positive proportion of those abelian surfaces are modular. And this, you may, if you haven't been keeping up with the work they've been doing, you might be familiar with an earlier paper by the same authors that appeared in 2023, where they proved a potential modularity result. This theorem is not simply an extension of that. It uses very different methods, and it's dramatically more powerful. I mean, potential modularity is nice, but actual modularity is a much stronger and a much more useful result. And yeah, at least from my perspective, an admittedly biased perspective, I would regard this as one of the most significant breakthroughs in arithmetic geometry, at least in the last decade. So if you're an arithmetic geometer, I urge you to go check out, and aren't familiar with this work, I urge you to go check out their paper. Even if you don't care about all the details of the proof, you can skip to the last 2 sections. I think they're sections 10 and 11, where they give a long list of wonderfully explicit applications. And if you're not an arithmetic geometer, another thing you could do is go read the recent Quanta article, which just appeared a few weeks ago about, what is it, Fermat's last theorem getting superpowered, or some title along those lines. But anyway, it's a fun write-up of this result. Of course, it perhaps oversimplifies things that its target audience is not an audience of number theorists. in any case, but it's still a fun article to read. The other place where we've made substantial progress is in step 4. And this is work by Raymond van Bommel, Shiva Chidambaram, Edgar Costa, and Jean Kiefer, all of whom did this work when they were members of the Simons collaboration in arithmetic geometry and number theory, who developed an algorithm for enumerating isogeny classes of abelian surfaces over Q that contain a Jacobian. They don't necessarily enumerate the entire isogeny class, but they will find all the Jacobians in the isogeny class. Currently, their algorithm is restricted to the generic case, which is arguably the hardest case, meaning Jacobians that don't have any extra endomorphisms, even over Q bar. But they're currently in the process of generalizing this algorithm to cover all Jacobians of genus 2 curves. Okay, so that and so for both steps 1 and 4, I'm actually fairly confident. I mean, it's easy for me to say this. I'm not the one who actually has to do the work to prove these theorems, but I'm fairly confident that, say, over the next course of the next decade, we will have more or less complete solutions to steps 1 and 4 of this algorithm. Unfortunately, step 2 is dramatically harder. There has been some heroic effort in this direction by Chris Poor and David Yuan. I'll say a bit more about that in a moment, to compute the analog of classical modular forms, which at least in the generic case for G equals 2 are called paramodular forms associated to automorphic representations of GSP4. But they're extremely difficult to compute. And sort of the nail in the coffin is the fact that even if we could solve that problem, we still can't use this algorithm because step 3 is literally impossible. There neither is nor can be an Eichler-Shimura-like correspondence that would allow us to go from an automorphic form to an abelian surface. Okay. So just to give you a sense of sort of how far we are, even if I rewind all the way back to 1972, more than 50 years ago, and ask at that point, this was 20 years, well, more than 20 years before any form of modularity for elliptic curves was proved. We had the Antwerp tables, which I showed you in previous slides, and those included nearly 1,000 elliptic curves and corresponding modular forms. By contrast, the current tables of rational weight 2 paramodular forms are provably complete only up to level 251. That includes a few, maybe a dozen or so paramodular forms, only one of which is actually the generic case, a GSP4, a modular form that we would expect to correspond to a generic abelian surface. And here by generic, I mean an abelian surface that doesn't have any extra endomorphisms. When you do have extra endomorphisms, I'll say a bit more about this in a few slides, you would expect to be able to find sort of a, quote, simpler automorphic source for your abelian surface. In the generic case, the first one shows up at level 249. And even in that case, we cannot prove that there is a corresponding abelian surface. We have a candidate. We have a very likely candidate, which is almost certainly modular, but we don't know how to prove that. We do know how to prove modularity for many other abelian surfaces of higher level, but in terms of getting a complete list up to a given level and conductor bound, at the moment, we do not have a single generic abelian surface included in that list. On the other side, I don't want to put all the pressure on the automorphic side. On the arithmetic side, where I have worked for much of the last 10 years, the situation is much better. The LMFDB contains a table of genus 2 curves over Q that is as complete as we could make it at the time. But that table skips the very first abelian surface that arises, the very first abelian surface over Q, which does arise as a Jacobian. It happens at level 121. It's not a generic case. Now, to be fair, there's a good reason for that. We were enumerating genus 2 curves of small discriminant. because nobody knows how to enumerate genus 2 curves in order by conductor. We don't really even know how to do that in order by discriminant, but we can at least search for genus 2 curves with the coefficients in a box and pick out the ones with small discriminant. The reason the LMFDB is missing the Jacobian at level 121 is that its discriminant, despite its conductor being as small as possible, you can't get any smaller than 121. That's a theorem. Its discriminant is quite large. And the reason is that the curve in question is actually x naught of 22. And you might wonder, wait, why isn't there a 2 dividing the conductor? And the answer is, well, there is a 2 dividing the discriminant. In fact, there's a 2 to the 12th that appears in the discriminant of this genus 2 curve. And when you multiply that by the power of 11 that appears in the discriminant also, which is more than 11 squared, you get a discriminant that's substantially bigger than 1,000,000, which was the cutoff that the LMFDB used. And this highlights another reason why things are harder when G is 2. For elliptic curves, and the primes of bad reduction for an elliptic curve are exactly the set of primes that divide the conductor, which is also equal to the set of primes that divide the discriminant. But for G greater than 1, that is no longer true. So even for G equals 2, it will very often be the case that the curve will have bad reduction at primes where its Jacobian has good reduction, meaning the discriminant will be divisible by primes that don't divide the conductor. And those primes can be arbitrarily large. I'll mention a little later in the talk, we have new tables of genus 2 curves, much larger tables of small conductor, not just small discriminant, about 6 million of them that we'll be adding to the LMFDB soon. They all have conductors less than roughly 1,000,000, 2 to the 20. But they include curves whose discriminants are hundreds of digits long. Minimal discriminants are hundreds of digits long. Some of them are divisible by primes over 1,000,000,000. Okay, so this is a thing that happens, and it's not a rare thing. It applies to about half the curves in our list. Okay, so just to highlight some of the things I've already mentioned, as I said, enumerating weight 2 pyromodular forms is very difficult. The main reason it's difficult is similar to enumerating classical modular forms of weight 1. We're sort of below the cohomological dimension. There's no dimension formulas. So even knowing whether there are any paramodular forms of a given level of weight 2 with a given level, setting aside the question of whether they have rational coefficients, is already a very hard problem. In fact, the reason this list is provably complete only up to level 251 is because at level 252, we can't actually prove that there aren't any, even though we believe there are not. Even if you can compute all the paramodular forms of a given level, what does it mean to compute? It typically means computing an explicit Fourier series that would be an analog of a Q expansion for your paramodular form. But unlike in the classical modular form case, that Fourier series, the coefficients that show up in that Fourier series, they're not Hecke eigenvalues. But to compute the L function, you actually need to know the Hecke eigenvalues. So that's sort of a separate additional problem. And the complexity of doing that grows with, the prime P, if you're thinking about the operator T sub P. And it grows quite rapidly. And in order to compute the L function, by which I mean computing enough coefficients so that you could, for example, determine or at least bound its order of vanishing at its central value, or compute special values, or just explicitly compute to high accuracy any value of the L function, you need a lot of coefficients. Something on the order of the square root of the conductor, but the leading constant is fairly large, at least for the LMFDB in genus 2, so these are degree 4 L functions. We want to have all the coefficients up to roughly 138 times the square root of the conductor, which means even in these very small ranges with conductors around in the hundreds, we need thousands of coefficients. Okay, and that's really out of reach of at least our current methods for computing paramodular forms. As I mentioned, there's no analog of the Eichler-Shimura construction, and this isn't just a gap in our knowledge. There can't be, because the converse of the modularity conjecture is false. By which I mean, so when I stated, maybe I didn't highlight this, when I wrote down the first modularity theorem for elliptic curves and rational new forms, it was in both directions. The set of these L functions is equal to the set of these L functions. When I wrote down the modularity theorem conjecture for abelian varieties, all I said is that every abelian variety is modular, that there is an automorphic form. I said nothing about the other direction, and that's because in the other direction, it's not true. It's not literally true. And the first place where that shows up already happens at g equals 2. You can have L functions of degree 4 that look like the L function of an abelian surface. Everything you might say to characterize the L function of an abelian surface is true about these L functions, but they're not the L function of any abelian surface. They're actually the square root of the L function of an abelian fourfold with quaternionic multiplication. And this is why the original statement of the paramodular conjecture by Brummer and Kramer, it was noted by Frank Caligari in a blog post that, for trivial reasons, this conjecture is actually false. And this is the trivial reason, that you can come up with QM abelian fourfolds. And if you look at the Euler factors that appear in their L function, they're all the square of an Euler factor that looks like the Euler factor of an abelian surface. And if you were to reduce down to the residue field, there would be an abelian surface there, but might be a abelian surface there, but globally there is not. I should mention the same thing in theory could have happened for elliptic curves. It doesn't happen because it's not possible for an abelian surface over Q to have quaternionic multiplication that's actually defined over Q. You can only have potential quaternionic multiplication. You need to base change to a quadratic field for it to actually arise. Okay. Another major challenge, I already said it was hard. Enumerating genus 2 curves by discriminant is hard. Enumerating them by conductor of their Jacobian is even harder. But even if you could do that, that's not enough, because not every abelian surface over Q can be realized as the Jacobian of a genus 2 curve over Q. So then you might say, well, we should really instead be just enumerating abelian surfaces, as abelian surfaces. But that is, not something that I want to try and undertake. I mean, the most direct way to generically represent an abelian surface is as a projective variety in P15 defined by 72 quadratic forms. And as I mentioned, no algorithm is known for enumerating genus 2 curves by conductor. And in fact, even computing the conductor of a single genus 2 curve over Q is not an easy thing to do. It is if the discriminant is odd. We have very efficient algorithms for computing the conductor exponent at all odd primes. These are implemented due to Qing Liu. These are implemented in Paris GP, thanks to work by Bill Allenbear. But 2 is a problem. And figuring out the exact value of the conductor at 2, we have algorithms that work in principle, but in practice, it's very difficult to make them effective. But I should say there is ongoing work in this area, and I expect this problem to be solved in the near future. But at least the current state of the art is we don't really have an effective practical algorithm for computing the conductor at 2. The most practical method is to instead infer the conductor at 2 using the functional equation, which I'm going to explain in a moment. Okay. All right, so if we don't want to work with a variety in P15 cut out by 72 quadratic forms, what should we do instead? Well, there are many different ways of realizing an abelian surface over Q. I mean, one very straightforward example is just as a product of elliptic curves. And, on the one hand, that might seem trivial, but it's good to do that because asymptotically, 100% of abelian surfaces over Q ordered by conductor are products of elliptic curves, just because there are more elliptic curves. If you count, at least conjecturally, I should say, that's not a theorem, but that's the expectation. We expect that there are on the order, if I count number of elliptic curves of conductor up to x, they're on the order of x to the 5/6 elliptic curves. And then if I were to count products, there would be something on the order of x to the 5/6 times log x. But if I were to instead count, say, genus 2 curves ordered by conductor under standard conjectures that the number should be roughly the same as if I ordered them by height, I get an x to the 7/10. Okay. Another way that you could get an abelian surface over Q is in the classical way. There is an Eichler-Shimura correspondence one can apply to a weight 2 nu form with quadratic Q expansion. And this will give you an abelian surface over Q. But it's not a generic abelian surface. It's going to have at least real multiplication. But in this situation, we have an easy way to realize these abelian surfaces. And not all of them can be realized as Jacobians. Sometimes there's a Mestre obstruction that will prevent us from realizing it as a Jacobian over Q. So this is good. Another easy way to get an abelian surface over Q is as the Bay restriction of an elliptic curve over a quadratic field. And of course, you can take the Jacobian, and most, one expects that most generic abelian surfaces should be realizable as a Jacobian, but not all of them. There are generic abelian surfaces that do not admit a principal polarization, and for that reason cannot be realized as a Jacobian. But one way you can realize them is as a prim variety. So you find a cover of curves, C1 and C2. The simplest case is where C2 has genus 1, not necessarily an elliptic curve. It doesn't have to have a rational point, but a genus 1 curve covered by a genus 3 curve. And then this will induce a map on their Jacobians, and the kernel of that map on the curve upstairs, the Jacobian of the curve upstairs, is an abelian surface. So there will be an isogeny factor of the Jacobian of the genus 2 curve that is an abelian surface over Q. And if you know the curve upstairs and the curve downstairs and can compute their L functions explicitly, that's not hard. We can compute the L function of that abelian surface without ever writing down explicit equations for the abelian surface itself. And I should mention, these options are definitely not mutually exclusive. In fact, it's possible to find Jacobians that are isogynous to all 5 of these examples at the same time. I mentioned principal polarization. That just means that our abelian variety is there's an isomorphism between the abelian variety and its dual, an isogeny of degree 1. In general, there's always an isogeny to the dual, but it doesn't have to have degree 1. So that degree is called the degree of the polarization. In cases 1, 3, and 4 that I listed here, that polarization is always principal. It's usually principal in case 2, occasionally not, but it's usually not principal in case 5. And that's why case 5 really is necessary if we want to get a sort of an explicit handle on abelian surfaces over Q. Modularity is already known in cases 1 and 2. That's another reason to seek this representation. If you can find a way to represent your abelian surface in those forms, then you're done with modularity. It's known in many cases for case 3. Whenever K is a real quadratic field, it's always known. And there's recent work that is now proving this for not yet all, but many imaginary quadratic fields. And as I mentioned, the work of Boxer, Caligari, Guy, and Poloni proves modularity for a positive proportion of case 4. That proportion is something on the order of 11%. But I expect that number to increase going into the future. Okay. Now, I realize most of you probably can't read the details of this slide, and I could summarize so this slide is meant to illustrate some of the different ways in which you can realize modular forms, automorphic forms corresponding to an abelian surface. And so the short version of this slide is, it's complicated. So you can organize abelian surfaces according to their real endomorphism algebras equipped with an action of Galois. This is the same thing as organizing them according to their Sauter-Tate group. And when you do that, it helps to sort of separate into cases in which you can describe more specifically a motive and a modular form that can arise for that type of abelian variety. And so you'll see in the far right column, you'll see modular forms. The generic case is a paramodular form, a modular form for GSP4, way 2. But you'll also see many CMFs, that stands for classical modular form, HMFs or Hilbert modular forms, BMFs or Bianchi modular forms. And there's all sorts of complicated ways in which they can be related via twisting and Galois actions. Okay, so this is work in progress that I hope will appear later this year, knock on wood. Joint work with Andy Booker, Jeroen Sijsling, John Voigt, and Don Yasaki. Okay, but now I want to state our main result. Proof is still in progress. This is joint with Andy Booker. But assuming modularity of abelian surfaces and the generalized Riemann hypothesis for Rankin-Selberg L function, there are at most 1,059 isogeny classes of abelian surfaces over Q of conductor up to 1,500. I say at most because there are 2 cases that we can't quite yet prove, but we know there's at least 1,057. So we are very close to having a complete list of L functions, which we know have corresponding paramodular, modular form, automorphic forms, and abelian surfaces of conductor up to 1,500. Which is an improvement over the 251 that I mentioned earlier, and includes many generic cases. So 818 of them arise from products of elliptic curves, 28 come from weight 2 new forms with a quadratic Hecke field. 7 of them are Weil restrictions of an elliptic curve over a quadratic field. And at least 204 of them arise from generic abelian surfaces, of which at least 193 include a Jacobian. And we think that 204 should really be a 206. So when we finish this proof, hopefully in the next month or so, we will ideally be able to remove everything that's in parentheses on these slides. The difficulty that we're having is, as I'll mention in a moment, finding the corresponding abelian varieties is hard, even once you know the L function. And there are also, the same method yields some additional results that are not provisional. These are now theorems. One I'm particularly fond of is a complete enumeration of isogeny classes of modular abelian surfaces over Q with good reduction away from 7. They're exactly 2. 7 is the unique prime for which we know such a statement. In fact, it's S equals the set containing 7 is the unique set of primes for which we have a provably complete list of abelian surfaces with good reduction away from S. And so this required enumerating L functions of conductor up to 7 to the 4th for reasons I'll explain. So that was up to level 2,401, but we didn't have to do all the levels. We just had to do all the levels that are power of 7. A similar result is we know the complete list of isogeny classes of modular abelian surfaces over Q with conductor dividing 2 to the 11. Now, I can't say we know everything with good reduction away from 2 because the power of 2 dividing the conductor can be as large as 2 to the 20, which is well beyond the range that we can currently apply our method. And I'll just mention here that Robin Visser's PhD thesis, which appeared recently published, attempts to give a complete enumeration of abelian surfaces, or at least Jacobians, that arise that have good reduction away from 2. And here's a list of the curves that he found and the number of isogeny classes. Prior to this work, we only knew that list was complete up to conductor 2 to the 9th, and now we know that it's complete up to conductor 2 to the 11th, but there's still a long ways to go to get to 2 to the 20. And Robin is here if you want to ask him questions about this result. Okay. All right, so in the last 15 minutes, I want to briefly explain how we proved these results. And I'm going to necessarily need to sweep a lot of details under the carpet, both for the sake of time, but also because the details are really complicated. And as I mentioned earlier, I'm not an analytic number theorist. And if I get too deep in the details, I'm likely to make a mistake. Okay. So what do we mean by L functions from nothing? Well, what we mean is we're going to set up a set of axioms or set of properties that at least the L functions we're most interested in, we believe they should all satisfy. And then we're going to use those axioms to explicitly enumerate all the L functions that satisfy those axioms under certain constraints on their conductor and root number and potentially other invariants. So our initial setup is we're going to consider L functions of degree 2g. For us, g is 2, so these are degree 4 L functions. Motivic weight 1, that just means they're L functions that could come from an abelian variety. They all have motivic weight 1. With rational field of coefficients, so their Dirichlet coefficients are integers that come from an Euler product. We're going to further assume that the completed L function that we can associate to this, where we're going to put in effectively an Archimedean Euler factor at the infinite prime, at the infinite place of the right form to match an abelian variety. That completed L function satisfies a functional equation in which we have an epsilon is the root number plus or minus 1. And this is also going to tell us the parity of the order of vanishing of our L function at its central point. And a conductor with n, which is a positive integer. And you could take so I haven't defined the conductor. I've been talking about conductors of abelian varieties. I haven't defined them. The simplest definition I know is it's the integer n for which this functional equation should be true. We don't know how to prove that yet. There is a completely arithmetic way to define both the root number and the conductor of an abelian variety, but it's complicated. And for our purposes, all we really care about is that they're the integers that make this functional equation true, or under the modularity conjecture, for our abelian variety. And we're also going to impose bounds on the size of our Dirichlet coefficients, which ultimately come from the Weil bounds. Although we can be slightly more precise at primes of bad reduction, we can do better than the Weil bounds. So as I mentioned, under the modularity conjecture, every abelian variety over Q of dimension G has such an L function. Conversely, if we assume that the L functions that we're interested in that satisfy these axioms actually come from the abelian variety, we can impose some additional constraints. In particular, we can fix a set of local root numbers, plus or minus 1, for each prime p dividing the conductor. And those will impose additional constraints on the shape of the Euler factors at those bad primes. And that's actually a useful thing to do. It speeds up our algorithm, so we're going to do that. So just to briefly say a few words about the conductor and why 7 is the unique prime for which we know all isogeny classes of abelian surfaces over Q with good reduction away from 7. We have explicit bounds on the powers of primes that can divide the conductor of an abelian variety of a given genus. And in genus 2, you'll see that you get you can have a 2 to the 20, a 3 to the 10, a 5 to the 9. All of those arise. There are examples in the LMFDB that, or we know examples that realize these. But then for p greater than 5, the largest power is p to the 4th. And so 7 to the 4th, if you restrict to a particular prime, is the smallest, largest power of the prime that could possibly divide the conductor. And so this is why we were able to prove our theorem for 7. Proving it for 11 would require us to go up to level above 10,000. And the same is true if we tried to do it for 3, 5, or 2. Okay. So what's our strategy? So let S of G n epsilon denote the set of L functions of degree 2G with a particular conductor n and root number epsilon. And we're always dealing with L functions that have integer real coefficients, so they're self-dual, so the real root number is always going to be plus or minus 1. Schaffer-Reivitz's conjecture, which was proved by Faltings, implies that this is a finite set. Moreover, there is an effectively computable integer n naught, roughly on the order of square root of n, for which the coefficients up to a sub n naught uniquely determine the L function in this as an element of the set. And under GRH, you can make that n naught much smaller, which is why we needed GRH in the theorem that I mentioned earlier. And our goal is an algorithm that takes as inputs these 3 integers, g, and for us, g is just going to be 2. This is the only version of the algorithm we've implemented so far. So g is 2, a conductor n, and a root number plus or minus 1. And then that algorithm will figure out a suitable n naught and output a list of distinct tuples of integers, a1, a2, up to a sub n sub naught, that uniquely describe the L functions in this set. Now, there has been prior work in this direction, some initially by my co-author Andy Booker, but especially by Farmer, Koutsouliadis, and Lemerle. They have a paper on abelian varieties from their L functions that describes exactly this strategy, sort of at this level. However, their work is entirely heuristic. They're not trying to prove anything. They're just trying to sort of heuristically compute L functions of abelian varieties that ought to exist. And their methods are not as efficient as the results I want to present, largely because they're not using as much information as we are, and also because they're not using all the computational infrastructure we're using, which includes using simplex solvers and very fast implementations of lattice reduction, the LLL algorithm, that allow us to go much further. But I think the most important part, and what I want to focus on in the last 10 minutes, is how we're able to get rigorous results out of this method, not just approximations. Okay. I should mention that our plan for enumerating L functions depends quite critically on our ability to compute this set very explicitly. because we need to know the cardinality of this set on the nose in order to know, because in order to actually complete our exercise, our goal is to enumerate a billion varieties. Knowing the L functions helps us to know how many isogeny classes of the billion varieties we need to find. But until we found them, we're not done. And so it's not just enough to even know the number we're looking for. We really want to know a lot of coefficients of the L function, because that will help us in our search for corresponding abelian surfaces. Okay, I just wanted to, just a very quick, brief digression. As I mentioned, the Shafarevich conjecture, which proved by faulting, says that for any fixed number field and any fixed set of primes, the set of abelian varieties of a given dimension G over that number field with good reduction away from primes in that set, that's a finite set. Perhaps a more well-known theorem, also due to faultings, is this proof of Mordel's conjecture, which says the number of rational points on a nice curve of genus greater than or equal to 2 over a number field, that's a finite set. And in fact, the proof of the second conjecture can be reduced to the proof of the first conjecture. The faulting's proofs of both these conjectures are ineffective. They tell us these sets are finite, but they don't give us an explicit bound on how big they can be or a method to actually enumerate these finite sets. And that's what our goal really is, to enumerate at least a special case of the finite set that arises in Shafarevich's conjecture. We currently do not know of any provable algorithm for enumerating these finite sets, not even in principle. However, there is recent work by Alpogé and Lawrence, who proved under a number of conjectures, including the Hodge conjecture, the Tate conjecture, and Fontaine-Mazer, the existence of an algorithm to do this. Now, this is very much an in-principle algorithm. I think in Levant's talk, he explained it as, well, the universe will end due to heat death many, many times before this algorithm terminates, even in the easiest case. But it's at least an in-principle algorithm to do this. Our results give you a different way of doing sort of the same thing. So under the modularity conjecture, so a different starting hypothesis, our algorithm will give you a similar method to enumerate abelian varieties of a fixed dimension with good reduction over a number field with fixed dimension with good reduction away from a fixed set. And thereby, that will imply an algorithm to explicitly compute the rational points on a curve of genus greater than or equal to 2. Our algorithm, for that purpose, our algorithm is also hopelessly impractical. But I think you could argue it's slightly less hopelessly impractical. And the reason I would say that is, so the work of Alpogé and Lawrence runs through the bottom of the diagram that I showed you in the first slide, going through the Galois representations, whereas we're taking the top route through the L functions. And I think the top route is slightly more efficient. All right. Okay. So how are we what is our algorithm? How does it work? So for each non-negative integer, we're going to define a certain test function. This comes from an inverse Mellin transform. And we have the functional equation is going to give us an identity that relates the value of this function s sub k, which uses our test function, and the Dirichlet coefficients of an L function we imagine might exist, and gives us an explicit identity coming from the functional equation. And this identity is valid for all positive values of x. And if we choose an appropriate k and set x to be equal to the square root of the conductor, or even we can do this with x very close to the square root of the conductor, we obtain a linear constraint on the Dirichlet coefficients on the a sub n. So these are the value of fk n over square root of n. These are real numbers. So we have some infinite series linear expression in the a sub n with real coefficients. However, these f sub k functions decay very rapidly. And we know that our a sub n's are not growing too quickly. They're growing much less quickly than n is. And this allows us to truncate this sum and get a very small interval about 0 on the right-hand side to cover the tail. And that interval constrains any possible L function. So we can treat the a sub n as variables when we do that. And so now this gives us a finite linear constraint with real coefficients on the a sub n's that have to land in some interval that's going to depend on our choice of test function, which I'm indexing by k, and a bound on how many n's we want to consider. Okay, and it turns out to be better to orthogonalize our test functions so that they're more independent. There's not as much redundancy between them. And we can also take advantage of additional constraints just on the size of the a sub n's. Those are going to impose some inequalities on our expressions. And to speed up the algorithm, we're also going to assume that our L functions are automorphic so that we can twist them by Dirichlet characters. And for each twist of our original L function with unknown a sub n, we get a new L function whose Dirichlet coefficients we can express in terms of the same a sub n's, and we get another linear constraint coming from that twist. Now, as the conductor of these characters gets bigger, the conductor of the twisted L function gets bigger, and the constraints become harder to work with. So we're only going to take a finite number of twists. But the upshot is we get a bunch of linear equations that constrain our a sub n. Okay. And so now we've reduced the problem to a linear algebra problem. And I just want to quickly run through one example that I hope will illustrate how this algorithm works. And we're going to focus on conductor 249, the example I mentioned where we don't actually know of the existence of a modular abelian surface. But I'm going to show you how we can prove the existence of an L function at level 249. And for this example, we're going to fix, so 249 is 3 times 83. We're going to fix local root numbers at 3 and 83. It turns out for any other choice of root numbers, it's easy to prove there are no L functions. So this is the one choice that's interesting. And for this example, we're going to truncate our Dirichlet series at 64. So we're going to consider A1, A2 up to A64. And in our setup, we get 5 linear constraints corresponding to 5 different combinations of Q, the conductor of our Dirichlet character, and K, the test function that we're using. So K is running up to 7, and we're only using 2 different twists, the trivial twist, which is our original function, and then one twist by the quadratic character of conductor 3. And I've written down explicitly the coefficients that in this linear system, at least to 3 digits of precision. And you can see that they are getting smaller by the time you get to A64. They're quite small. And then I'm also explicitly giving you the interval that we know they're contained in. That interval is always going to contain 0, because if we didn't truncate, it would be exactly equal to 0. The size of that interval is really determined by the bound on our error term. But we're not going to solve this linear, we're not going to try to solve this linear system. I mean, it doesn't have a unique solution, obviously. What we're going to do is use it, we're going to use the simplex method to try to determine bounds on the first coefficient, on a sub 2. A priori, we know that a sub 2 from the May bounds could be anything between -4 and 4. We'd like to constrain that to a smaller interval. And so we could think of these 5 equations as cutting out hyperplanes in some space of dimensions, maybe a priori, maybe dimension 63. And we could use the simplex method to try to maximize or minimize A2 subject to these constraints. But in order to get a rigorous result, we actually want to work with the dual problem, which amounts to finding a linear combination of these 5 constraints that we should expect that corresponds to maximizing or minimizing A2. And so it turns out if you run a standard simplex solver, it will spit out this vector with 5 entries. The vector that it spits out might not be perfectly right. We're going to run this at fixed precision, say 128 bits of precision, or maybe even 80 bits of precision, because we don't actually care if this vector is perfect, because we're going to apply this vector to these linear constraints using interval, and then use interval arithmetic, assuming worst case bounds on all of the coefficients other than A2. And this is going to give us an interval that provably has to contain A2. And in the case, it turns out on the minimizing doesn't help us at all. The bound is no better than -4. But on the upper bound, it improves it from 4 to -1. And so this eliminates 5 of the 9 possibilities for A2. There are 4 left. Okay, and now we try plugging in all 4 of those possibilities. And we run the exact same algorithm again. Here, we're going to use the multiplicity of the Dirichlet coefficients. Once we know what A2 is, we also know what A4, we also know most of the even coefficients, and we can move them to the right-hand side. And so the A4 and A8 are going to disappear from our linear expression. And now we run the algorithm again, and we get a dual vector, a dual solution for minimizing and maximizing A3. And assuming, in this case, I've assumed A2 was -4, and subject to that assumption, there are only two possibilities for A3. Now we try A2 is -3, and we find there are three possibilities for A3. And we try -2, we find there are two possibilities for A3. And we try -1, and we find there is actually no possible choice for A3. There's no way to extend with A2 equals -1. So even though we didn't know, we couldn't rule out -1 for A2 initially, our constraints on A3 will force us to discard this value of A2. And so by trying all the values of A2, we now have a list of 7 initial prefixes of length 3 for A1, A2, A3. And now we proceed from here. We try all 7 of those and then try to get bounds on the next coefficient, which will be A5. Okay? And eventually, by the time we get up to A7, there's only one possibility left. We now know that every L function of conductor 249 with local root numbers 3 and 83 of -1 starts with a specific sequence of Dirichlet coefficients of length 7. And at this point, when we're down to one solution, rather than continuing to go coefficient at a time, we're going to use LLL to speed things up. LLL is very good at finding integer lattice points in a parallelepiped that may have very large dimension. And at this point, we expect that parallelepiped coming from our constraints to contain exactly one point. Okay, so just to summarize the computation so far, you can view it as a tree where we started with A1 as 1. The possibilities for A2 ran from -1 to 4. And then for each of those, we had possibilities for A3, et cetera. But there was only one branch of this tree that we could continue past A7. And by increasing the value of M, we get a system with 738 unknowns and 219 constraints. Now we're using Ks up to 77 and Qs up to 24. So a much larger, more complicated system. But modern implementations of the LL algorithm can handle systems of this size very efficiently. And it actually only takes a few seconds to extend our unique prefix of length 10 up to a unique prefix of length 1,000. And we can go further than 1,000. Okay. And I think in the interest of time, I'm just going to jump to the next slide, which shows you the timings. The 249 example I showed you is one of these little purple dots over here, which took maybe 2 seconds. But this is a logarithmic scale. So if you go to that dot on the very far right, that's for conductor 1489, that's about 50 CPU years of computation. Okay, so this is an exponential time algorithm, at least in the worst case, and these worst cases are all prime values. But if you're an optimist, you can maybe imagine that the sort of the typical case, the median case, might be slightly less than exponential. Maybe it's sub-exponential. Okay, and then the last step is proving completeness. And there's a very clever trick for doing this to Andy Booker, which is to suppose that our list is, so what are we worried about? We're worried about that our finite prefix is actually realized by 2 different L functions of 2 different automorphic forms. We want to prove that can't happen. Well, we suppose there are 2 different automorphic forms. We take their Rankin-Selberg convolution. This is an L function of larger degree. And that L function will be entire as long as the L functions of the 2 automorphic forms have no common factor. If they do have a common factor, we can divide that out and we've reduced to the G = 1 case where everything is known. And if they don't, we can construct an inequality that this Rankin-Selberg convolution L function must satisfy. And then we can show the inequality is violated by computing enough L coefficients, by making n not big enough. And once we do, we've proven that there can't be 2 different automorphic forms realizing with the same L function prefix. Okay, I think I will skip the search for the abelian surfaces and just thank you for your time.